Hi guys. So I'm sorry I'm out today. My sister just had this adorable, cute little baby here, so I'm crazy excited. This is my first nephew. I'm an aunt, so I'm sorry I can't be there, but um, I'll be back soon. I promise. Okay, so today we're going to be talking about motion and forces, but first you need to take a force diagram quiz from last class. So go ahead and pause this video, write this down, and then go to this link and do it. All right, pause. Okay, we back? So hopefully you've taken that quiz. Hopefully you did awesome. P.S. You can go take it again if you need to. Now, last time we talked about Newton's first law, and we said that things are going to keep doing what they're doing unless there's some net force, some total force on that object. So today we're going to talk about what happens when there is one of those total forces. So force, mass, and acceleration are all related. To get something to accelerate, to get it to change what it's doing, how it's moving or not moving, then we have to apply a force. And the bigger that force is, the more the object will accelerate. So if you have like a baseball player throwing a baseball and you have like a 3-year-old throwing a baseball, well, the baseball player should be able to get it to go faster from rest to super fast when especially if they're pitching. But a 3-year-old can't apply as big of a force, so it's not going to have as big of a change in velocity. So greater force means greater acceleration. And remember, acceleration is a change in velocity. Now, if you have the same force on two different masses, then think about like throwing a baseball versus throwing a bowling ball and throw them the same way so you have the same force that you're exerting on them. And which one do you think is going to speed up the most? You're probably not going to get a bowling ball to go very quickly if you throw it overhanded. But a baseball, you can get to accelerate a lot more. So smaller mass with the same force means bigger acceleration. Bigger mass with the same force means smaller acceleration. So we have this law, an equation that says how that works. So force on an object equals the object's mass times however much it's going to accelerate. And we know from last time that force is measured in newtons because Isaac Newton did a lot of this stuff with forces, so we named the unit after him. Mass in this formula has to be in kilograms. You've got to use it in kilograms. It doesn't work if you use grams. Then acceleration is always our standard meters per second squared, or meters per second per second. So copy that down. Now, now that we learned a new formula, we're going to try a practice problem, of course. So we start every practice problem, no matter what, writing down our givens. Well, let's see. This one, mass is 10 kilograms. Ooh, my stylus is awful. Sorry about that. And we have an acceleration here of 9.8 meters per second squared. And we're asked, what is the force on that object? So we pick our formula, and since we just learned this one, we just pick a formula with force, mass, and acceleration, but it happens to be the one we just learned. Woohoo! And all you got to do here, since force is already isolated, we've already solved it for force, then you can just plug in your numbers. So plug in mass of 10 kilograms and acceleration of 9.8 meters per second squared. And then we multiply our numbers. So 10 times 9.8 is 98. And then our units here, you can't just put the units together like we've done in the past. It's got to be newtons. So you're going to have to start really memorizing these units. So we have a force of 98 newtons on this object. So let's try one that's a little bit different. And remember, you can pause the video anywhere and copy this stuff down. So we've got this object that is accelerating at a rate of 9.8 meters per second squared. You'll see why I'm using this 9.8 a lot. It just happens to be a super, super useful common number. And the force on the object in this case is 49 newtons. And we want the mass this time. So we have our formula with all three of these variables. Our two givens and our unknown. Force equals mass times acceleration. And we want to get mass by itself in this case. So we're just going to divide both sides by acceleration so that it cancels out on the right. And we're left that mass is by itself. And mass is equal to force over acceleration. So now we can just plug in our givens. Our force was 49 newtons. Our acceleration was 9.8 meters per second squared. So our mass, when we divide our numbers, we should get 5, right? And our units aren't really going to cancel or do anything weird, so we just have to know in this formula, mass is measured in kilograms. So that's all there is to it. You're going to have a worksheet that goes over a lot of these problems, and it also does the force diagram thing with the arrows that we did the other day, where if they're in the same direction, then you're going to add them together. If they're opposite directions, then you subtract them from each other and figure out the net force, that total force. And then you'll have to solve some of these problems. All right, now a few more forces you need to understand. Friction is any force that opposes motion, goes against motion, tries to keep things from moving or slow things down when they are moving. So if some objects are really sliding past each other, then we call that sliding friction. Pretty simple. But if two objects are pushing against each other, like if you're pushing something really heavy along the floor, but it just won't budge, we call that static friction, like stationary friction. It prevents things from sliding against each other. Then we have things like rolling friction. So when you have a wheel for that like tire to get traction, it's actually not slipping along the ground. If you have traction in your car tires, then you don't want your wheels to slip. You want them stationary against the ground so that they can roll and move forward. So rolling friction is what your course calls the friction with wheels, except it's really a type of static friction. So, and then there's fluid friction, what your curriculum calls fluid friction. And that's just like, we're talking mostly about air resistance. We might have some like friction of something moving through water, but usually we don't have to deal with that very much. So air resistance is when objects are moving through air. If you wave your hand really quickly back and forth through the air, you can actually feel that air resistance opposing your motion. Now, if you do it slowly, then you don't really feel that air resistance. So air resistance depends a lot on the speed of the object. So if it moves through more air per second, then you got more air resistance. It also depends on the size and shape of the object. So if that object has a bigger volume, takes up more space, then you're going to get more air resistance on it as it moves. If it takes up less space, then you're going to have less air resistance. So if you take like a piece of paper and just drop it and it flutters to the ground, there's a lot of air resistance on the surface of that paper, making it go slower. But if you take that same piece of paper and crumple it up into a ball, so its surface area is less, you change its size and shape, then you can drop it and it doesn't have as much air that it has to pass through. So air resistance is going to be lower. It's going to fall faster. Now, we need to talk about one more thing, what makes things fall in the first place, and that is gravity. So gravity is an attractive force, and gravity is between really any two objects with mass, but we're going to talk mostly about gravity on Earth. So on Earth, the force of gravity is going to accelerate all objects downward toward this Earth at the same rate, at this gravitational acceleration, G. So this formula here might look familiar, and it was F equals ma, but if we're talking about gravity, we just use this constant G for our acceleration, and it's just this number 9.8 meters per second squared that we plug in to our formula for acceleration. So make sure you copy that down. So everything no matter how massive it is, has the same acceleration from gravity. If we don't have air resistance to slow things down, then things fall at the same rate. There is a video you're supposed to watch next about dropping a bowling ball and a feather in a vacuum, and they actually fall at the same rate. They hit the ground or hit this crate on the bottom at the same time. It's craziness. All right, so if you hear force of gravity, then that's obviously calculated with this formula, Fg equals m times g, that one. But the word weight is just another word for force of gravity, gravitational force. So whenever you have a problem and it gives you like the mass of an object, and somebody says, oh, calculate its weight, well, you're just going to plug in for acceleration. You're going to calculate the force of gravity and plug in for acceleration, this 9.8 meters per second squared. Super simple. So if I say something has a mass of, let's say, I don't know, 10 kilograms. Didn't we just have a problem like that, I think? And I want to know its weight. Well, you're just going to plug in mass of 10 kilograms, 9.8 meters per second squared for your g acceleration, and you're going to get that weight equals 98 newtons. So pretty simple, pretty straightforward. But if I say weight, don't tell me an answer in pounds. It better be this force in newtons. So weight is a force, and we talked about how if something isn't falling at that same rate, that 9.8 meters per second squared, then there is air resistance acting on it. So you can see from this elephant and the feather that are falling. The elephant falls fairly quickly because he has a very big mass, and yes, he takes up a lot of space, but air resistance can't be as big of a force. It's not as big of an effect on him. But this feather, the feather, like air resistance is a huge factor. Even though it starts accelerating toward the ground, air resistance is going to cancel out that force, and will not completely cancel it out, but it's going to take away a lot of it, and you're going to have a much slower acceleration. So if something isn't falling that quickly, air resistance is the reason why. All right, so that's all I had for you today. You'll watch that video with the bowling ball and the feather, and then you've got a worksheet to do. And if you happen, that is going to be collected. So if you happen to finish early, then there are some practice problems in the textbook to do. So I will see you in a couple days. Have an excellent Wednesday. Bye.